Hello, and welcome back. I'm Alex. Tonight, I want to share something fascinating with you: how quantum physics just completely breaks all the rules we thought we knew. And trust me, it's oddly relaxing to think about before sleep. So grab a pillow, get settled, and let's explore this together. If you end up enjoying it, I'd really appreciate a like and subscribe. All right, let's dive in. Last night you came home, opened the door, stepped inside, normal stuff. But if you were a photon, you'd have just gone through the door and simultaneously passed through the wall at the same time. No, I'm not talking about science fiction. I'm talking about an experiment recognized by the Nobel Prize. Over the next few minutes, I'm going to prove to you that this impossible thing is an everyday reality at the quantum level. Let me show you exactly what I mean. Picture a simple experiment, one that's been run thousands of times in labs around the world. You have a source that fires photons, tiny bullets of light, one at a time. In front of this source, there's a barrier with two slits cut into it. Behind that barrier sits a screen to catch wherever the photon lands. Now here's what you'd expect to happen. You fire one photon. It goes through either slit 1 or slit 2. It can't go through both because, well, it's one particle. Fire enough photons, and you should see two bright strips on the screen, one behind each slit. Simple, right? That's what common sense tells us should happen. But that's not what happens. Instead, the screen shows multiple strips of light, an interference pattern. Think about that for a second. One photon, two slits, but the pattern that emerges looks like waves crashed into each other and created ripples. It's like throwing one marble through two doorways, but somehow the marble creates a pattern, as if two marbles collided mid-flight. The only way this makes sense is if the single photon went through both slits at the same time. It interfered with itself. One particle taking two paths, simultaneously meeting itself in the middle. If you were a photon walking into a bar, you could be at the beer counter and at the pool table at the exact same moment. That's not a magic trick. That's quantum physics. But wait, because it gets stranger. What happens if you try to peek? What if you place a detector at each slit to see which path the photon actually takes? Surely you'll catch it going through one or the other, right? Here's where everything collapses. The moment you add those detectors, the interference pattern vanishes, gone. Now you just see two strips of light, exactly what common sense predicted in the first place. The photon stops going through both slits. It picks one like a normal particle should. The photon somehow knows you're watching, and it changes its behavior accordingly. It's like a child playing when no one's looking, breaking all the rules, jumping on the furniture. But the second they know there's a camera recording, they sit down and behave perfectly. Except a photon doesn't have eyes. It doesn't have a brain. It doesn't have any way of knowing whether you're observing it or not. And yet it does know, or at least it acts like it does. This isn't a flaw in our equipment. This isn't us disturbing the photon with clumsy measurement tools. This has been verified over and over with increasingly sophisticated technology. The act of observation itself changes what the photon does. Before you look, it's behaving like a wave spread across both slits. After you look, it's behaving like a particle going through just one. The implications are staggering. It means that at the quantum level, reality itself isn't fixed until someone observes it. The photon exists in multiple states, doing multiple things until the moment of measurement forces it to choose. So why does a particle of light do this insane thing? To understand that you need to forget everything you think you know about what matter is, you need to stop thinking of particles as tiny solid objects bouncing around, because that's not what they are. Not really. And the answer to this mystery lies somewhere you'd never expect. It lies in a vibrating guitar string. Yes, guitar. I'm not joking. But before we get to guitars and strings, there's something fundamental about the universe. You need to understand first. Something your brain is going to resist with every fiber of its being. Before we talk about strings, there's a truth about the universe you need to know. A truth that your brain is going to reject violently, because your brain has been programmed to live in the macro world, the world of big things, the smooth world, the world where everything flows continuously from one state to another without any gaps. But that's not how the universe actually works at the smallest scales. Let me give you a thought experiment. Imagine you're running at 10 kilometers per hour. Now slow down to half that speed, 5 kilometers per hour. Keep having 2.5, 1.25, 0.625. Here's the question. Is there a limit? Or can you keep dividing your speed forever, always finding a smaller number, a slower speed, going on infinitely? Classical physics says you can divide forever. There's always a smaller number. It's like a ruler. The closer you look, the finer the gradations you can see. You could theoretically measure down to infinitely small increments. Everything is smooth, continuous, infinitely divisible. But quantum physics says something completely different. It says at some point you hit a wall. You can't divide any further. The universe doesn't allow it. There's a hard stop. The universe isn't analog, it's digital. Now this sounds absurd. Your everyday experience tells you otherwise. You can move at any speed you want. Water flows smoothly from a tap. A car accelerates gradually from 0 to 60. Everything in the world you see appears continuous. But zoom in far enough down to the level of atoms and electrons, and suddenly the rules change. Suddenly, the universe starts operating in discrete chunks, like climbing a staircase instead of walking up a ramp. You can be on step 3 or step 4, but never in between. Let me give you a concrete example that's been proven in laboratories. Take an electron orbiting a hydrogen atom. That electron can have an energy level of negative 3.6 electron volts, or it can have an energy level of negative 3.4 electron volts. But under no circumstances can it have an energy level of negative 3.5 electron volts. That state simply does not exist. It's not that we haven't measured it yet. It's not that our instruments aren't precise enough. It's that the universe forbids it. There is no halfway point. Think of it like an elevator. The elevator stops at the 3rd floor. It stops at the 4th floor. But it never ever stops between the 3rd and 4th floors. That in-between space doesn't exist in the elevator system. You can't press a button for floor 3.5 because there is no floor 3.5. The universe works the same way. The energy levels are discrete floors. Electrons can only occupy certain levels. The spaces in between simply aren't real. It's like your bank account showing 100,000, 50,000, or 20,000. Never 37,500. Except your bank account works that way because humans designed it. Quantum mechanics works that way because that's the fundamental law of the universe. This discreteness, this chunkiness at the smallest scales, is where the word quantum comes from. It derives from the Latin word quantus, meaning how much. From the same root, we get quantity, the idea of counting discrete amounts. A quantum is a discrete packet of energy, the smallest possible unit that can't be divided further. Energy, momentum, and other properties at tiny scales don't flow smoothly. They jump in steps in chunks in quanta. And this is why physicists call it quantum mechanics. It's mechanics because it operates by rules, by steps like gears clicking into place. It's not the smooth flow of water. It's the precise ticking of a clock each tick, a discrete moment, no in-betweens. So why? Why does the universe choose to operate this way? Why does it switch from smooth and continuous at large scales to chunky and discrete at small scales? What's the underlying reason? The answer lies in music, or more specifically, in the mathematics of vibrating strings. Because when you pluck a guitar string, something remarkable happens. The string doesn't just vibrate at any old frequency. It can only vibrate at specific frequencies, discrete harmonics, 1 wave, 2 waves, 3 waves, but never 1.5 waves. The string itself enforces this rule. And it turns out particles in the universe follow the exact same principle. They're not little solid balls. They're vibrations, standing waves, patterns of energy that can only exist at certain frequencies. The universe is quantized because waves can only resonate in certain ways. Just like a guitar string can only produce certain notes, particles can only occupy certain energy states. The rules of waves dictate the rules of matter. And that's what we're diving into next. The secret hidden in those vibrating strings. The key to understanding why quantum physics destroys common sense and rebuilds reality from the ground up. So let's talk about those guitar strings, because they hold the secret to why particles act the way they do. Have you ever plucked a guitar string? If you have, you've accidentally touched one of the deepest secrets of the universe. You don't need to know how to play guitar. You need to understand how guitar plays with physics. When you pluck a guitar string, something fascinating happens beneath the surface. The string doesn't just vibrate randomly. It does something very specific, something that mirrors exactly what particles do at the quantum level. Here's what happens. You pluck the string. A wave travels down its length toward one end. When it reaches that end, it can't just disappear. The wave reflects back, traveling in the opposite direction. Now, you have 2 waves on the same string, one going left, one going right, moving through each other. This is where the magic happens. If the frequency is just right, these 2 waves resonate perfectly. They create what physicists call a standing wave, a wave that appears to stand still, even though it's actually the result of 2 waves continuously moving through each other. The standing wave has a beautiful stable shape. It might have one peak in the middle. That's your fundamental note, the deepest tone the string can produce. Or it might have 2 peaks, giving you an octave higher. 3 peaks, you get a 12th. 4 peaks, 2 octaves. the pattern continues. But here's the critical part. You never get 1.5 peaks. You never get 2.3 peaks. Those states simply cannot exist on a vibrating string. Why not? What's stopping the string from vibrating at those in-between frequencies? The answer lies in how waves interact. For a standing wave to form and persist, the wave traveling in one direction must perfectly match the wave traveling in the opposite direction. They need to align in frequency, in wavelength, in timing. When they do, they reinforce each other, building up that stable standing pattern. But if the frequency is even slightly off, something different happens. The two waves start fighting each other. Sometimes they add together, sometimes they cancel out. But the pattern keeps shifting, unstable, chaotic. Eventually, the interference destroys itself. The energy dissipates. The wave collapses. Only certain frequencies allow the waves to harmonize perfectly. Only certain patterns can sustain themselves. Everything else self-destructs. Think of it like two people dancing tango. They need to move in perfect sync, matching each other's rhythm, each other's steps, each other's breathing. One step out of time, and they're stepping on each other's feet. The dance falls apart. A guitar string is pickier than you might think. It only accepts relationships that work in perfect harmony. Now here's where it gets profound. This isn't just about music. This is about the fundamental structure of reality. Because particles, those tiny building blocks of everything you see and touch, behave exactly like standing waves on a string. Remember those energy levels we talked about? The electron in a hydrogen atom that can have negative 3.6 electron volts or negative 3.4, but never 3.5. That's not arbitrary. That's not the universe being random or picky for no reason. It's because electrons are standing waves. Just like the guitar string can only vibrate with 1 peak, 2 peaks, or 3 peaks, electrons can only exist at certain energy levels. The in-between states are like trying to make a guitar string vibrate at 1.5 peaks. The wave pattern simply can't sustain itself. It's not stable. It doesn't work with the physics of waves and resonance. The parallel is direct and beautiful. Standing waves on a string are quantized. They come in discrete numbers of peaks. Energy levels of electrons are quantized. They come in discrete values. It's the same principle, the same underlying mathematics playing out at different scales. Particles are standing waves. That's the revelation. They're not little solid balls bouncing around in space. They're patterns of energy, vibrations that can only exist at certain frequencies, certain configurations, certain quantum states. And here's the deeper insight. The universe doesn't choose to work this way. This isn't some arbitrary rule that got written into the cosmic code. It's a natural consequence of how waves behave. Just like a guitar string doesn't choose to only ring at certain notes, it's simply the result of waves traveling, reflecting, and interfering with each other. The laws of waves dictate the laws of matter. Resonance creates reality. Every electron in your body right now is vibrating at its own specific frequency. Every proton, every neutron, every quark, all of them are standing wave patterns, humming at the precise frequencies allowed by the mathematics of wave interference. You are a symphony, 7 octillion atoms, each one playing its note, all of them harmonizing together. to create the complex, stable pattern that is you. You're not just made of particles, you're made of music, quantum music, the kind that plays itself on strings too small to see, but too fundamental to ignore. But here's the thing, the universe is far more complex than a few simple notes on a guitar string. Reality isn't just a handful of pure tones. It's rich, it's intricate, it's endlessly varied. Galaxies and proteins and consciousness and thunderstorms. How do you create all of that complexity from simple vibrating strings? How do you get from a few basic waves to everything? That's where the real magic begins. And it involves a trick discovered by a French mathematician studying heat. Our hero is a man named Jean-Baptiste Joseph Fourier. He was born in France. In 1768, lived through the French Revolution, served as a scientific advisor to Napoleon during the Egyptian campaign, and eventually became a mathematician studying of all things heat transfer. Not the most glamorous topic, but while investigating how heat flows through materials, Fourier discovered something that would change mathematics, physics, and ultimately our understanding of reality itself. He discovered that any complex wave, no matter how intricate or irregular, can be broken down into a sum of simple sine waves. And crucially, it works in reverse. Combine enough simple sine waves together, and you can create any wave pattern you want, any shape, any complexity, any structure. It's like language. You don't need to memorize 16 million words to communicate every possible thought. You just need 26 letters. From those letters, you can write every story ever told and every story yet to be imagined. Fourier found the same principle in waves. A few basic building blocks, infinite possibilities. This is called wave superposition, and the rules are beautifully simple. When two waves meet, they don't bounce off each other or destroy each other. They pass through each other, and while they overlap, their effects add together. If both waves are rising at the same spot, they add up. You get a bigger wave. If one wave is rising while the other is falling, they cancel out. You get nothing or something smaller. Think of it like two people pushing a door. If they both push from the same side, the door swings open with twice the force. If they push from opposite sides, the door stays still. The forces cancel. Now imagine you have two sine waves with the same frequency perfectly in sync. When the first wave reaches its peak, so does the second. When the first dips to a valley, the second does too. They're in phase, as physicists say. Add them together, and you get a wave that's twice as tall, twice as powerful. They reinforce each other. But shift one wave slightly, move it half a wavelength over, and suddenly when the first wave peaks, the second wave is in a valley. They're out of phase. Add them together, and they cancel perfectly. The result is a flat line, no wave at all. The energy hasn't disappeared, it's still there in the individual waves, but the combined effect is zero. This might seem like a mathematical curiosity, but it's actually the key to creating complexity from simplicity. Take two waves, you get one new pattern. Take 10 waves with different frequencies and phases, you get something far more complex. Take 100 waves, carefully chosen and combined, and you can create virtually any shape you can imagine. Let me give you some concrete examples to help you visualize this. First, consider a square wave. This is the kind of wave you see in digital electronics, a signal that's either fully on or fully off, jumping between two values with sharp right-angled corners. It looks nothing like a smooth flowing sine wave. But here's the magic. You can create a square wave by adding together sine waves. Start with a fundamental frequency, one complete up and down cycle. Then add another sine wave at 3 times that frequency with 1/3 the amplitude. Then add another at 5 times the frequency with 1/5 the amplitude. Keep going 7 times, 9 times, 11 times. The more sine waves you add, the more the result starts to look like a square wave. The corners get sharper, the flat tops get flatter. With enough sine waves, you can make it perfectly square. Even though every single component is a smooth, curving sine wave, it's like drawing a circle using straight lines. Use 4 lines, you get a square. 8 lines, an octagon. 64 lines, it's looking pretty circular. 1,000 lines, you can't tell it's not a perfect circle. Complexity emerges from adding simple pieces. Now let's look at something even more relevant to particles. Imagine you want to create a pulse wave, a single spike of energy at one location with flat silence everywhere else. Just one peak, sharp and localized, surrounded by nothing. How do you create that from sine waves that stretch out infinitely in both directions? You need a lot of them. A lot. You need sine waves of many different frequencies, all carefully arranged. At the point where you want your spike, all these waves need to be in phase, all rising together. They constructively interfere, adding up to create a tall, sharp peak. But everywhere else, the waves need to be out of phase with each other. Some rising, some falling, all canceling each other out through destructive interference. The result is silence, flatness, nothing. The more waves you include, the sharper and more localized your spike becomes, and the flatter the silence everywhere else. And this is where it clicks. This localized spike of energy, this convergence of many waves at a single point, this is what a particle is. A particle isn't a tiny, solid ball rattling around in space. It's the meeting point of countless waves, a place where wave energy converges briefly, coming together before spreading out again. Think about that for a moment. Every particle you've ever encountered, every electron, every photon, every quark, is actually a convergence point for waves. It's an interference pattern, a spot where many different wave components happen to be in sync, creating a localized peak of energy. The particle isn't a thing. It's an event, a temporary gathering of waves that gives the appearance of a localized object. Now let's connect this back to something Einstein told us. His most famous equation, E equals mc squared, says that mass and energy are equivalent. They're the same thing in different forms. You can convert mass into energy, as happens in nuclear reactions. You can convert energy into mass, as happens in particle accelerators. But what does that actually mean? What is mass if it's really just energy? Now we understand. Energy is waves, propagating through space, spreading out, traveling. Mass is waves, converging, at a point, coming together, concentrating. Same thing, different configuration. You weigh 60 kilograms, let's say. But fundamentally, you're not made of matter in the traditional sense. You're 60 kilograms of energy temporarily at rest, temporarily concentrated into the pattern we call a human body. Every atom in your body, every particle that makes up those atoms, is a spike of wave energy, a convergence point that holds together because the waves interfere in just the right way to create a stable pattern. You're not a thing. You're an event, an ongoing process, a pattern of energy that maintains itself from moment to moment. Every morning when you wake up, in a very real sense, you're rematerializing from wave energy. The pattern that is, you reforms the waves, align the interference creates the peaks we call particles, and those particles arrange themselves into atoms, molecules, cells. It's like a video game character spawning into existence, except it's real. It's happening. It's the fundamental nature of what you are. And here's the beautiful part. This isn't some abstract mathematical trick. This is measurable, testable, verifiable physics. The equations work. The predictions match experiments. Particles really do behave like wave interference patterns. Mass really is condensed energy. You really are a standing wave pattern that somehow looks in a mirror and calls itself by a name. Okay, so now we know that particles are waves, interference patterns, convergence points of energy, but there's still a problem. If a particle is made of many waves coming together, then where exactly is that particle? And where is it going? Because that's where things get truly strange. Stranger than anything we've talked about so far. Picture this. You're sitting in a cafe, lost in thought, staring at your phone, and then your crush walks by, just passes right through your field of vision. In that half-second moment, your brain desperately wants to know two things. Where are they, right now, at this exact instant? What's their position, and where are they going? What direction? How fast? What's their momentum? In the normal world, the world of coffee shops and sidewalks and people, this is easy. You just look. You can see exactly where they are and exactly where they're headed. Both pieces of information available simultaneously. No problem. But in the quantum world, the universe makes you choose position or momentum, location or speed. You can know one with precision, but the moment you do the other, becomes fuzzy, uncertain, unknowable. It's like a video game that only gives you one skill. You can either activate, see location, or see speed, but never both at once. Choose wisely, because the universe won't let you have both. This is Heisenberg's uncertainty principle, and it's not a measurement problem. It's not that our instruments are too clumsy or our techniques too crude. This is a fundamental law of reality. The universe itself doesn't allow both properties to be precisely defined at the same time. And here's the beautiful part now. That we understand particles as waves, we can finally see why. Let's start with the first case, a long, smooth wave. Imagine a perfect sine wave stretching across space, rising and falling in a regular, predictable pattern. The wavelength is clear. You can measure the distance from one peak to the next. The frequency is clear. You can count how many cycles pass by in a given time. And here's the crucial connection. In quantum mechanics, a particle's momentum is directly related to its wavelength. The shorter the wavelength, the higher the momentum. The longer the wavelength, the lower the momentum. This relationship is precise and mathematical. Know the wavelength perfectly, and you know the momentum perfectly. So for this long, smooth sine wave, we have perfect information about momentum. We know exactly how fast this particle is moving and in what direction. But what about position? Where is the particle? Well, the wave has peaks everywhere along its length. It extends across space, rising here, falling there, rising again over there. If the peaks represent possible locations for the particle, then the particle could be anywhere along that wave. It's spread out. You know your crush is walking at 5 kilometers per hour. Great, but they're somewhere along a 2-kilometer long street. Where exactly? You have no idea. The speed is precise, but the location is fuzzy, smeared out across a huge range. And here's the deeper truth. That's easy to miss. This isn't just, we don't know where it is. The particle really is spread out. It genuinely exists in a distributed state across that entire wave. Remember the double-slit experiment? Remember how the photon went through both slits? At the same time, this is why, when the particle is in a long wavelength state with well-defined momentum, it's also in a spatially extended state. It's genuinely in multiple places at once, because it is the wave, and the wave is everywhere. The particle is vibing, as you might say. It hasn't settled down into a specific location yet. It's exploring possibilities existing in a superposition of positions, all while maintaining a very precise momentum. Now, let's look at the opposite case. What happens when you want to pin down the particle's position to create a localized spike? A particle that's clearly in one spot, and nowhere else. You need to combine many waves, 10 waves, 20 waves, 100 waves, all with different wavelengths, all converging at a single point. At the point of convergence, all these waves are in phase. They rise together, creating constructive interference, building up a tall, sharp peak. That's your particle, right there, precisely localized. But everywhere else, the waves are out of phase with each other, some rising, some falling, canceling each other out through destructive interference. The result is flatness, silence, nothing. The particle is definitely not there. So now you have excellent knowledge of position. The particle is at this specific location, sharp and well-defined. But what about momentum? You've got 10 different waves converging to create this spike. Each wave has a different wavelength. And since momentum is related to wavelength, each wave represents a different momentum. One wave might correspond to moving left slowly, another to moving right quickly, another to moving left quickly. They're all mixed together. It's like standing at an intersection with 10 roads branching out in different directions. You know exactly where your crush is standing, right here at this spot. But which of these 10 roads are they about to walk down? You have no idea. The information about direction and speed is now distributed across multiple possibilities. The more precisely you want to pin down the particle's location, the more waves you need with different wavelengths. And the more waves with different wavelengths you include, the more uncertain the momentum becomes. This is the trade-off. This is the fundamental nature of the universe. It's not a limitation of technology. It's not something we'll overcome with better equipment. It's the rules of the game. The universe doesn't allow you to have both a perfectly sharp spike in position and a perfectly defined wave in momentum, because those two states are mathematically incompatible. You need a spread out wave to have defined momentum. You need many converging waves to have defined position. You can't have both. And here's the truly mind-bending implication. The universe itself doesn't know exactly where a particle is until someone asks. Think about what it would take to perfectly specify a particle's position. You'd need waves coming in from every possible direction and wavelength, an infinite number of them, all precisely calibrated to create a spike at exactly one point. To know all those wave components, you'd need information from across the entire universe. The gravitational effects of distant galaxies, the electromagnetic fields from every star, the quantum states of every other particle in existence. To know precisely where one electron is, you'd need to know everything about everything. Heisenberg wasn't being poetic when he called it the uncertainty principle. He meant it literally. The universe operates on approximations most of the time. It keeps things fuzzy, probabilistic, spread out in waves. It only sharpens the picture, only collapses the wave into a definite state when something forces it to, when an interaction demands a specific answer to the question where. It's like a spreadsheet that doesn't calculate a million decimal places unless you specifically ask for that precision. The universe is computationally efficient. It doesn't waste effort on unnecessary exactness. Now let's bring this full circle. Let's go back to the double-slit experiment, because everything we've learned makes it finally beautifully clear. When you don't observe which slit the photon goes through, you're leaving the photon in case 1. It's a spread-out wave with well-defined momentum. The wave naturally extends across space, meaning it genuinely goes through both slits simultaneously. Momentum is precise, position is fuzzy. The two parts of the wave interfere with each other on the far side, creating that telltale interference pattern on the screen. But when you do observe which slit the photon goes through, you're forcing case 2. You're asking the question, where? You're demanding that the photon have a specific position. To answer that question, the wave function has to collapse into a sharp spike. Multiple wave components converge at one slit or the other. The photon becomes localized, position becomes clear, but momentum becomes uncertain. And once the photon is localized to one slit, it no longer goes through both. It can't interfere with itself because it's no longer spread out. The interference pattern disappears. You get 2 simple bands of light, one behind each slit, exactly what you'd expect from particles that pick one path or the other. It's not that the photon knows you're watching. It's not magic or consciousness or some cosmic awareness. It's that the act of measurement forces wave convergence. It transforms case 1 into case 2. It changes the fundamental nature of what the particle is doing. It's like asking someone, "Do you love me?" The question itself changes the answer. Before you asked, the relationship existed in a superposition of possibilities, undefined fluid. The moment you ask, you force a collapse into a definite state, yes or no. And the relationship is different afterward than it was before, simply because the question was asked. Observation isn't passive in quantum mechanics. It's an interaction, and interactions change things. So what are particles really? What are they doing? They're not little objects traveling from point A to point B, like marbles rolling across a floor. That's not how it works. They're waves spreading out from point A, propagating through space as extended probability distributions, exploring multiple paths simultaneously. Then something happens, an interaction, a measurement, a convergence of wave components. The wave collapses into a localized spike at point B. The particle arrives, and then the wave spreads out again, radiating from that new point. ready for the next collapse, the next arrival, the next manifestation as a localized particle. Particles don't travel, they dissolve and reform. They spread and converge. They exist as events, not objects. And you're made of these particles. Trillions upon trillions of them. Every electron, every quark, every photon interacting with your cells. All of them constantly shifting between wave and particle states, spreading out as probability clouds, and collapsing into definite positions billions of times per second. Every moment, the atoms in your body are dissolving into probability waves, and every moment, they're collapsing back into the solid, tangible form you recognize as yourself. You're not a thing that persists unchanged through time. You're an event that keeps happening over and over, a pattern that rebuilds itself moment by moment. You're not a noun. You're a verb. Not a snapshot, but a movie. Not a sculpture, but a dance. Every morning, when you wake up in a very literal sense, you re-emerge from the quantum foam. The probability waves that make up your atoms spend the night spread out in fuzzy superposition. And then interactions with light, with air, with the mattress beneath you, force those waves to collapse back into particles, those particles to arrange into atoms, those atoms to form molecules, those molecules to build cells, those cells to constitute you. You are an ongoing event, a process, a pattern of energy that knows its own name, and that more than anything else we've talked about tonight is what quantum physics reveals. Reality at its deepest level isn't made of stuff, it's made of happenings. Particles aren't things that exist, they're things that occur. You aren't a collection of objects, you're a collection of events. An ongoing symphony of quantum occurrences, each one a collapse of possibility into actuality, each one a moment where the universe asks itself where and finds an answer briefly before dissolving back into everywhere and asking again. That's what you are. That's what everything is. Waves that gather spike into existence and scatter over and over, forever ongoing. And somewhere in that endless gathering and scattering in that eternal dance of waves, becoming particles, becoming waves, consciousness emerged. You emerged. The universe found a way to look at itself and wonder why. So, particles are waves that collapse and reform, spreading and gathering in an endless dance. Beautiful, profound. But here's a question. What happens when humans try to harness quantum weirdness for something practical, like keeping secrets? 2,000 years ago, Julius Caesar had a problem. He was leading armies across Gaul, fighting battles far from Rome, and he needed to send messages back to his generals and allies. Strategic information, troop movements, plans of attack, the kind of stuff that if it fell into enemy hands could lose him a war. So Caesar came up with a trick, a simple one, but effective for its time. Whenever he wrote a message, he'd shift every letter of the alphabet 3 spaces to the right. A becomes D, B becomes E, C becomes F, all the way through with X, Y, and Z, wrapping back around to ABC. Take a phrase like, Astrum is great, and put it through Caesar's cipher. It becomes DVWXPLVJUHTW. Looks like gibberish. Sounds like the secret password for some mystery cult. But if you know the trick, if you know to shift everything back 3 spaces to the left, the message reveals itself instantly. This is encryption in its most basic form. Scramble the message using a rule. Share the rule with trusted people. Anyone with the key can unscramble it. Anyone without the key just sees nonsense. For Caesar's time, this was reasonably secure. Most people couldn't read at all, let alone decode a cipher. And even if an enemy intercepted the message, they'd have to figure out the system, which wasn't immediately obvious if you'd never seen it before. But here's the weakness, and it's glaring. There are only 26 letters in the alphabet, so there are only 25 possible shifts. Move everything, 1 space, 2 spaces, 3 spaces, and so on. At most, you'd need to try 25 different arrangements before one of them started making sense. A dedicated person could crack Caesar's cipher in minutes. Just brute force it. Try every possibility until words appear. This approach to breaking encryption, trying every possible key one after another until something works, is called a brute force attack, and it's a valid strategy as long as there aren't too many possibilities to check. Think of it like trying to unlock your bedroom door when you've forgotten the key. If you've got 25 keys on a key ring, you just try each one. Annoying, sure. Time-consuming, maybe. But totally doable. Security through obscurity only works when the obscurity is actually, obscure. Caesar's cipher is about as secure as a bedroom door lock. Fine for keeping out casual snoops. Useless against anyone determined. Over the centuries, cryptographers got more sophisticated. They realized that if the problem with Caesar's cipher was that it kept the alphabet in order, just shifted, then why keep the alphabet in order at all? Why not scramble it completely? This led to keyword ciphers. Here's how they work. Pick a keyword. Let's say quantum. Write out that keyword, removing duplicate letters, so QUANTM. Then, write the rest of the alphabet in order after it. That gives you a completely jumbled alphabet to use as your cipher key. Instead of a simple shift, every letter maps to a different letter in unpredictable ways. A might become Q, B might become U. There's no pattern to guess. You either know the keyword or you don't. And here's where the numbers get interesting. There are approximately 43 septillion ways to arrange the alphabet. That's 43 followed by 24 zeros. If you tried to brute force a keyword cipher by checking every possible arrangement, 1 per second, it would take you longer than the age of the universe. Much longer. So problem solved. Right? Encryption is secure forever. Not quite. Because the weakness isn't the number of possibilities. The weakness is that you don't actually need to try them all. You see, languages have patterns. In English, the letter E appears way more often than the letter Z. Certain letters commonly appear together. TH, ER, in on. Others rarely do. You don't see QX or ZJ very often. If you analyze a long enough encrypted message, these patterns start to show through the cipher. Frequency analysis, it's called. A skilled cryptanalyst doesn't brute force the 43 septillion possibilities. They look for patterns, make educated guesses, narrow down the options. With enough text and enough time, even a keyword cipher can fall. But then computers arrived, and everything changed. When humans started building machines that could calculate the entire battlefield of encryption and code breaking transformed overnight. If a human trying to crack encryption is like someone tapping on a door with a hammer, a computer is a jackhammer. Relentless, fast, tireless. Modern CPUs can perform trillions of calculations per second. Trillions. Let that sink in for a moment. The keyword cipher that would take a human longer than the universe's lifetime to crack. A computer still can't brute force it quickly. Trillions are still nowhere near septillions. But the gap is a lot smaller than it used to be. And more importantly, computers can run sophisticated algorithms that narrow down possibilities in ways human brains never could. They can spot patterns in encrypted text at scales impossible for manual analysis. They can coordinate attacks across multiple machines, distributing the workload. Suddenly, ciphers that seemed unbreakable became vulnerable, not immediately crackable, but vulnerable enough that intelligence agencies and militaries started worrying. There's a persistent fear, maybe justified, maybe paranoid, that somewhere the CIA or NSA has secret supercomputers churning through encrypted communications, brute forcing their way into messages people thought were secure. So cryptographers had to evolve again. They needed encryption methods that didn't just rely on having a lot of possible keys. They needed methods where even if you had unlimited computing power, even if you could try 1 trillion keys per second forever, you still couldn't break the code in any reasonable time frame. This led to modern encryption systems like RSA, named after the initials of its inventors Reves Shamir and Adelman. RSA works on a beautifully simple mathematical principle. Take 2 enormous prime numbers, and when I say enormous, I mean hundreds of digits long. Multiply them together. The result, called the modulus, becomes part of your public key, the part you can share openly with the world. Here's the clever bit. If someone wants to decrypt a message encrypted with RSA, they need to know which 2 prime numbers were multiplied together to create that modulus. They need to factor it back into its prime components. And here's the beautiful thing. There's no known efficient algorithm for factoring large numbers into primes. None. You can't just run a formula and get the answer. The only way we know how to do it is to try dividing by prime numbers and see what works. It's sophisticated trial and error. For small numbers, factoring is easy. 42 equals 2 times 3 times 7. Simple. But for a 600-digit number, that's the product of 2 300-digit primes. Even the fastest supercomputers would take thousands of years to factor it. So RSA encryption seemed secure. Not because the key was hidden, the public key is literally public, but because reversing the math was impossibly hard. You could have all the computing power in the world and still make no progress. Encryption had apparently won the arms race. The mathematics of prime factorization created a wall that even computers couldn't scale. Messages could be sent safely. Financial transactions could be protected. Secrets could stay secret. Except there's a fatal flaw in all of this. A vulnerability that no amount of mathematical cleverness can solve. The encryption itself might be unbreakable. The mathematical problem might be impossibly hard, but you still have to give people the key. Think about it. You've encrypted your message with the most sophisticated algorithm ever devised. The cipher is mathematically perfect. Brute force attacks would take millions of years. Frequency analysis is useless. The encryption is airtight, but your friend on the other end needs to decrypt it, which means they need the key, and that key has to travel from you to them somehow. Email, that can be intercepted. Text message, same problem. Encrypted channel. Sure, but how did you exchange the keys for that encrypted channel? At some point somewhere, keys have to move from one person to another through a space that might not be secure. It's like installing a 10-ton titanium safe with a lock that's impossible to pick. Great security, except you have to mail the combination on a postcard. Anyone who intercepts that postcard can open your safe, and all your sophisticated security becomes worthless. This is the key exchange problem, and it's plagued cryptography since the beginning. No matter how strong your encryption, if someone can intercept and read your key during transmission, they can decrypt your messages. The whole system collapses. For decades, this seemed like an unavoidable weakness. You either had to meet in person to exchange keys securely, which isn't practical for most situations, or you had to take the risk that your key might be intercepted in transit. But then scientists started wondering, what if we could use the strange properties of quantum mechanics to solve this? What if we could create a key exchange system where any attempt to intercept the key would be detectable, where the very act of eavesdropping would leave evidence? Because remember, quantum particles change when you observe them. The photon in the double-slit experiment behaves differently when measured. What if we turned that vulnerability into a feature? What if we made the key itself out of quantum particles, specifically photons, and sent them in such a way that anyone trying to intercept and read them would inevitably disturb them? We could detect the disturbance. We'd know the key had been compromised. We could throw it away and generate a new one, repeating until we had a key we knew was secure. And then once we had that secure key, we could use it to encrypt our actual message and send that through normal channels. The message could travel by internet, by radio, by any conventional means. It wouldn't matter if someone intercepted it, because without the key they couldn't decrypt it, and we'd know the key was safe because quantum mechanics guaranteed it. This is quantum key distribution, and it sounded like science fiction, unhackable communication based on the fundamental laws of physics themselves. But there was a catch, one that nobody talks about much, and it has to do with what happens when quantum computers enter the picture. So you've got your encryption, RSA military, grade mathematically perfect, the kind of encryption that would take every computer on Earth working together for centuries to crack. Your message is scrambled so thoroughly that even if someone intercepts it all, they see as meaningless noise. You're secure, right? Not even close. Because here's the thing, nobody tells you about encryption. The strength of the lock doesn't matter if you're handing out copies of the key. You could have a 10-ton titanium vault with a combination lock designed by the world's best security experts, utterly unpickable, completely impenetrable. But if you email the combination as plain text, you might as well have left the door wide open. That's the encryption paradox. The math protecting your message might be perfect. The cipher might be unbreakable, but your recipient still needs to decrypt it, which means they need the key. And that key has to travel from you to them somehow. How do you send it? Email that passes through multiple servers, any of which could be compromised. Text message, same problem. Phone call, could be tapped. Encrypted channel, sure, but how did you exchange keys for that encrypted channel in the first place? It's turtles all the way down. Every secure channel needs a key, and that key needs to be exchanged through another secure channel, which needs its own key. Eventually, somewhere, you have to make a leap of faith. You have to send a key through a space you don't fully control and hope nobody's watching. And if someone intercepts that key, if they manage to copy it without you knowing, then every message you send afterward is compromised. They don't need to break your encryption. They don't need supercomputers or brilliant mathematicians. They just need your key. And suddenly, all your sophisticated security collapses like a house of cards. Have you ever felt that little spike of anxiety when sending a password through a text message? That moment where you think, is this safe? Could someone be reading this? That's your instinct recognizing the fundamental vulnerability of key exchange. You're not paranoid. You're just aware of how fragile digital security really is. Throughout history, this problem has haunted cryptographers. During World War II, the Germans used the Enigma machine, a mechanical cipher device that was incredibly sophisticated for its time, but they still had to distribute code books, physical books listing the daily key settings. Allies didn't break Enigma by solving the mathematics. They broke it by capturing U-boats and stealing the code books. The weakest link wasn't the encryption. It was the key exchange. Modern cryptography tried to solve this with something called public key encryption, the system behind RSA. You have two keys, a public key you share openly and a private key you keep secret. Someone can encrypt a message with your public key, but only you can decrypt it with your private key. Clever, right? Except even this system has vulnerabilities. How do you know the public key you received actually came from who you think it did? What if someone intercepted it and swapped it with their own public key? Now, they can decrypt messages meant for you, and you'd never know. You need certificate authorities and trust chains and elaborate verification systems, each one introducing new points of potential failure. The key exchange problem seemed unsolvable. It was the Achilles heel of cryptography. No matter how strong your armor, there's always that one vulnerable spot. But then quantum mechanics offered something remarkable. Not just better security, but security based on the fundamental laws of physics themselves. Security that didn't rely on mathematical difficulty or computational complexity. Security that relied on the fact that observing a quantum system changes it. Remember the double-slit experiment? Remember how the photon behaved differently when you watched it versus when you didn't? That wasn't a bug. That was a feature waiting to be exploited. Here's the idea. What if you encoded your encryption key into the quantum states of photons and sent those photons to your recipient? Not regular photons carrying regular information, but photons in carefully prepared quantum states, superpositions of polarization or spin. If someone tries to intercept those photons and measure them to read the key, the act of measurement collapses the quantum state. The photon changes, and because of the uncertainty principle, the eavesdropper can't measure the photon's properties without disturbing them. They can't copy the quantum state perfectly. They can't read the key without leaving traces. You and your recipient can compare a portion of your received photons, checking for disturbances. If the quantum states match what you sent, nobody intercepted them. If they don't match, someone was eavesdropping. The quantum mechanics itself tells you whether your key is secure. It's like sending a letter with a tamper-evident seal, except the seal isn't made of wax or tape. It's made of the fundamental uncertainty of quantum mechanics. Anyone who opens the letter to read it can't close it back up in exactly the same state. You'll know they peaked. This is quantum key distribution. And the beautiful thing is, once you've used it to establish a secure key, you can use that key with conventional encryption methods. Send your actual message through the internet, through email, through any normal channel. It doesn't matter if someone intercepts it, because without the key, they can't decrypt it. And the key is safe because quantum mechanics guaranteed it. The solution to humanity's oldest cryptographic problem came from the particle wave duality of photons, from Heisenberg's uncertainty, from the strange quantum properties that destroy common sense but build unhackable communication. And recently, China proved this wasn't just theoretical speculation anymore. In 2016, China launched a satellite called Messius, named after an ancient Chinese philosopher. It weighed just over 600 kilograms and carried equipment to generate and measure quantum entangled photons. Then, in March of 2025, they announced something remarkable using a newer, smaller satellite called MOSI, 23 kilograms, barely heavier than a large suitcase, and it had just successfully distributed quantum encryption keys across 12,900 kilometers from Beijing to a university near Cape Town in South Africa. That's nearly a third of the way around the planet. Quantum key distribution, working at a scale nobody had achieved before. Here's how it works. The satellite generates pairs of entangled photons, particles whose quantum states are linked together in that spooky way quantum mechanics allows. Remember, entanglement measure 1, photons polarization, and you instantly know the others, no matter how far apart they are. The satellite sends one photon from each pair to Beijing, the other to Cape Town. Each location receives a stream of photons, and each photon carries part of the encryption key encoded in its quantum state. Now here's the crucial part. If someone tries to intercept these photons mid-flight, if they try to measure them to read the key, the act of measurement disturbs the quantum state. The photon's properties change. It's no longer in the superposition state it started in. The entanglement breaks. The information gets scrambled. On the receiving end, the teams in Beijing and Cape Town can compare portions of their photon streams. They check whether the quantum states match what the satellite sent. Through statistical analysis, they can determine whether their photons were observed during transmission. If nobody watched the statistics look one way, if someone did watch the statistics look different, the math is precise, the detection is reliable. Eavesdropping leaves a signature written in probability distributions and correlation functions. It's like sending a letter with an incredibly sophisticated trap built in. Not a tripwire or an alarm, something subtler. The letter is made of special paper that changes color if anyone other than the intended recipient looks at it. You can't read it without the chemical composition of your eyes altering the ink, and the recipient can test the ink to see if it's been changed. That's quantum key distribution, and it sounds perfect, doesn't it? Unhackable by the laws of physics themselves. China's demonstration showed it could work at continental scales. MOSI, tiny and efficient, proved you could launch networks of these satellites. You could create a global quantum communication infrastructure. Every financial transaction, every government communication, every sensitive message could be protected by quantum keys distributed from space. Imagine a world where privacy was guaranteed by physics, where no hacker, no matter how skilled, no intelligence agency, no matter how well funded, could intercept your communications without you knowing, where true security existed because the universe itself enforced it. For anyone who values privacy, it seems like utopia, the end of surveillance, the triumph of secure communication, the final victory of encryption over code breaking. But there's something nobody's talking about, a problem that undermines the whole beautiful idea, and it has to do with what quantum key distribution actually protects. The quantum keys are unhackable, yes. The distribution method is secure, verified by the uncertainty principle itself. If anyone intercepts your quantum key, you know about it. You throw that key away and generate a new one. Eventually, you get a key you're confident is safe. Perfect so far. But then what? You use that key to encrypt your actual message. And here's the thing. You don't send the message through the quantum satellite. You can't. Quantum systems are notoriously bad at transmitting large amounts of data. They're great for keys, small pieces of information, but terrible for full messages, documents, videos, anything substantial. So you send your encrypted message through conventional channels, the internet, radio, fiber optic cables, normal everyday communication, infrastructure. And that encrypted message sitting on a server somewhere, traveling through cables stored in backups, that message is vulnerable to brute force attacks. Not attacks on the key distribution, those are impossible. Attacks on the encryption itself. The quantum key distribution protects the key. It doesn't protect against someone ignoring the key entirely and just trying every possible decryption until something works. But wait, you might say. That's what encryption is for. RSA takes thousands of years to brute force. It's mathematically secure. Except it's not. Not anymore. Because there's a new player in town. A technology that can shatter mathematical security. Like glass, quantum computers are coming, and they're going to break everything we thought was safe. Here's the uncomfortable truth about quantum key distribution. It protects the key brilliantly. Physics itself guarantees that nobody can intercept your key without you knowing. That part works flawlessly. But the encrypted message, the actual data you're trying to keep secret, that's still sitting out there, scrambled by conventional encryption, vulnerable to anyone with enough computing power to brute force their way through it. It's like installing a steel-reinforced door on a house made of straw. Sure, nobody's getting through that door, but they don't need to. They can just walk through the walls. For decades, this didn't matter because brute force attacks on strong encryption were impractical. RSA encryption with large enough keys would take conventional computers thousands, millions, even billions of years to crack. You could intercept an encrypted message, store it, and spend the rest of human civilization trying to decrypt it without success. The math protected you, not because it was impossible to break, but because it was impossibly time-consuming. But quantum computers change everything. In 2019, Google claimed their quantum computer, a device using supercooled qubits in carefully controlled superposition states, performed a calculation in 200 seconds that would take the world's most powerful, conventional supercomputer 10,000 years. 10,000 years compressed into 3 minutes. That's not a marginal improvement. That's a fundamental transformation of what computation means. And here's what keeps cryptographers awake at night. Quantum computers are exceptionally good at exactly the kind of mathematical problems that underpin modern encryption. Factoring large numbers into primes, the problem that makes RSA secure becomes trivial for a sufficiently powerful quantum computer. Something that would take a conventional computer millennia takes a quantum computer minutes, maybe seconds. Suddenly, all that data encrypted with RSA, all those messages protected by the mathematical difficulty of prime factorization, becomes readable. The encryption doesn't just get weaker, it becomes essentially transparent. Your bank transactions, your medical records, your private communications, government secrets, corporate intellectual property, everything encrypted over the past decades, all of it stored somewhere in server farms and backup systems, waiting to be decoded the moment someone builds a quantum computer powerful enough. And quantum computers already exist. They're in laboratories at Google, IBM, and government research facilities. They're not science fiction. They're engineering problems being solved right now, getting more powerful every year. Within a decade, maybe less quantum computers will be commercially available, not to everyone initially, but to well-funded organizations, intelligence agencies, tech giants, eventually hackers. The timeline is uncertain, but the outcome isn't. Quantum computers will break conventional encryption. It's not a question of if, it's a question of when. And here's where it gets truly disturbing. There's nothing stopping malicious actors from collecting encrypted data right now today and just holding on to it. Financial records, classified documents, private messages, anything encrypted that might still be relevant in 10 or 15 years. They can't read it now, but they don't need to. They just store it. Wait for quantum computers to become available, then decrypt everything at once. A delayed action data breach affecting decades of supposedly secure communications. Passwords you thought were safe, secrets you thought were buried, transactions you thought were private, all of it suddenly exposed years after the fact when a quantum computer finally gets pointed at the archived data. So what's the solution? How do you defend against a threat that makes your current security obsolete? You might think quantum key distribution is the answer. After all, that's quantum secure, right? Physics guarantees the key can't be intercepted. But as we discussed, quantum key distribution only protects the key exchange. Once you've got the key, you still encrypt your message with conventional algorithms. And those algorithms are vulnerable to quantum attacks. The quantum secure key doesn't help if the encryption itself can be broken. It's the wrong defense against the wrong attack. The real solution, somewhat anticlimactically, isn't quantum technology at all. It's better algorithms, specifically post-quantum algorithms, encryption methods designed to resist quantum computer attacks. the National Institute of Standards and Technology in the United States, recognizing the threat, has been running a competition for years to develop and standardize encryption methods that quantum computers can't efficiently crack. They're not relying on quantum mechanics to protect data. They're relying on mathematical problems that remain hard even when you have quantum computational power. One example is their FIPS 204 standard, which uses something called lattice-based cryptography. Instead of relying on the difficulty of factoring primes, it relies on finding specific patterns in mathematical lattices, points arranged in high-dimensional space. Imagine trying to find a particular path through a maze. Now imagine that maze exists in 5 dimensions, or 10 or hundreds. The number of possible paths explodes. There's no known algorithm, quantum or classical, that can efficiently search that space. You can throw all the qubits in the world at the problem, and it doesn't help. The maze is just as confusing whether you're a conventional computer or a quantum one. No shortcut exists. No clever quantum trick makes it easier. You're back to brute force trying, path after path. And the number of paths is so astronomically large that even quantum computers can't search them all in reasonable time frames. It doesn't matter how strong your computational muscles are if you don't know where to punch. And just like that, we're back where we started. A new technology emerges that threatens security. Hackers get new tools. Encryption experts develop new defenses. The arms race continues. Computers threatened privacy, then restored it with stronger encryption. Quantum computers threaten privacy again. Post-quantum algorithms restore it once more. Each breakthrough on one side drives innovation on the other. The cycle repeats, endless, exhausting, necessary. The universe gave us quantum key distribution, a glimpse of truly secure communication based on fundamental physics. But it also gave us quantum computers, a tool to shatter the encryption we thought was unbreakable. Both gifts, both curses, depending on who wields them. So are quantum satellites ushering in an era of guaranteed privacy? Probably not. Even if the key exchange is perfect, there's always another way in. Hackers are creative. Systems have vulnerabilities. Human error exists. Has quantum computing ended secrecy forever? Also no. Cryptographers are already pivoting to post-quantum algorithms. Defenses are being built. The walls are going back up. The truth is, security has never been absolute. It's always been a moving target, a competition between those trying to hide information and those trying to reveal it. Quantum technology just changes the playing field. It doesn't end the game. And so, the dance continues, encryption and decryption, hiding and seeking building walls and finding doors. The tools change, the mathematics evolves, but the fundamental dynamic remains the same as it was in Caesar's time. Some secrets stay hidden, some get revealed, and the line between them shifts with every new discovery, every new technology, every new understanding of what the universe allows and what it forbids. So quantum mechanics protects secrets, then quantum computers break them, then new algorithms protect them again. The cycle never ends. But all of this encryption and computation and security, it's all being done by conscious beings making choices, which raises a deeper question: where does consciousness come from in the first place? 35 years ago, a collection of atoms came together in a very specific arrangement. Oxygen, mostly. 65% of the total mass to be exact, but also carbon 18.5%, hydrogen 9.5%, nitrogen 3.5%, a bit of calcium and phosphorus for structure. These elements combine all the time throughout the universe. Oxygen bonds with hydrogen to make water, carbon chains together to form complex molecules. Calcium builds minerals. Nothing unusual about any of these processes. Chemistry happens. Atoms interact. Compounds form. But what was unusual about this particular collection of atoms is that it eventually got up one day and decided to call itself by a name. My name specifically. The elements that constitute me somehow became aware that they constitute me. The same thing happened to you, and to everyone you've ever known, and to everyone who has ever lived. A pile of stellar dust carbon forged in the cores of dying stars, oxygen created in supernova explosions, hydrogen left over from the Big Bang somehow arranges itself into a pattern complex enough to look around and think, I exist, which when you really sit with it is decidedly strange. How does what is essentially rocks and air and water develop a sense of identity? How does matter become aware of itself? This is the consciousness problem, and it might be the deepest mystery we face. We can map the human brain down to individual neurons. We can trace neural pathways and measure electrical activity. We can watch regions light up when you think about different things, but we still can't explain why any of that activity produces the subjective feeling of being you, the sensation of experiencing the world from inside your skull. Philosophers call these subjective experiences qualia, the redness of red, the painfulness of pain, the you-ness of you. And despite centuries of investigation, we still don't know where they come from or why they exist. So let me ask you this. Where exactly did consciousness enter the equation? At what point in your development did you become aware? When you were a fully formed adult? When you were a child? When you were a newborn? When you were still in the womb? Go back further. Were you conscious as an embryo? As a cluster of cells? As a single fertilized egg? Probably not, right? At some point, consciousness wasn't there. And then gradually, or maybe suddenly, it emerged. But where's the line? When exactly does a collection of cells become conscious? Is it when the brain forms? When neurons start firing? When neural networks reach a certain complexity? And here's where it gets truly weird. If consciousness emerges from brain activity, from neurons firing electrical signals, then how many neurons do you need? 100 billion, the number in a human brain. 1,000,000? 1,000? Just one. Because if consciousness is the result of electrical and chemical activity in neurons, and if a single neuron firing represents the smallest unit of brain activity, then does one neuron firing constitute a tiny fragment of consciousness? And if a neuron's activity is just electrons, moving ions, flowing, electrical charges shifting, then are electrons themselves slightly conscious? Is consciousness a property that goes all the way down to the quantum level? Or is there some threshold, some critical mass of complexity below which consciousness simply doesn't exist, and above which it suddenly does? And if so, where's that threshold? Who gets to be conscious and who doesn't? These aren't just abstract philosophical questions. They have real implications. If you're building an artificial intelligence, at what point does it become conscious? If you're deciding which animals deserve ethical consideration, How do you determine which ones are aware enough to suffer? We have strong intuitions about consciousness in other humans. We're pretty confident our fellow people are aware, experiencing the world, having thoughts and feelings. We can't see inside their minds, but we assume they're conscious. Because they're like us, they behave like us, they tell us they're conscious. But our certainty starts to waver after that. Are dolphins conscious? Probably. Are dogs? Most people would say yes. Are ants harder to say? Are bacteria? Almost certainly not right. Except we're just guessing based on behavior and similarity to ourselves. We don't actually have a test for consciousness. We don't have a measurement. We operate on belief and feeling and instinct. And here's the uncomfortable truth. Consciousness might not be an on-off switch. It might be a spectrum. You might have more consciousness when you're awake than when you're asleep. A chimpanzee might have less consciousness than a human, but more than a mouse. An insect might have a sliver of awareness, just enough to respond to stimuli, but not enough for what we'd recognize as thought. Or maybe everything has a tiny amount of consciousness. Every neuron, every cell, every electron. And what we experience as human consciousness is just what it feels like when trillions of these tiny conscious moments combine into a unified whole. Some physicists and philosophers actually believe this. There's a term for it, panpsychism. The idea that consciousness is a fundamental property of matter like mass or charge present at every level, but only noticeable when organized into sufficiently complex systems. It sounds ridiculous. Electrons don't think. Atoms don't ponder existence. But then again, how else does consciousness arise? From non-conscious matter? Where's the magical threshold where dead stuff becomes aware? Maybe there is no threshold. Maybe awareness goes all the way down. Maybe you are what it feels like when oxygen and carbon and hydrogen organize themselves into a particular pattern, and that pattern becomes complex enough to recognize itself. Maybe consciousness isn't something that emerges. Maybe it's something that was always there in every particle, every interaction, every quantum event, just waiting for the right configuration to amplify it into something we'd recognize as a mind. But if consciousness is distributed across all matter, then we need to ask who actually qualifies as conscious enough to count researchers studying animal behavior ran a survey. They asked scientists who work with various species a simple question: do you believe the animals you study are conscious? The results were fascinating, not for what they revealed about animals, but for what they revealed about human uncertainty. 92% of respondents were willing to say that non-human primates, apes and monkeys, possess consciousness. Makes sense. They're close relatives. They use tools. They recognize themselves in mirrors. They have complex social behaviors. If anything is conscious besides humans, it's probably them. But that number dropped to 73% for other mammals. Apparently, being a mammal isn't enough on its own. You need to be the right kind of mammal, smart enough, social enough, similar enough to us. For birds, 61%. For octopuses, 64%. These are intelligent creatures, capable of problem solving and learning, but they're so different from us that we start to lose confidence. Maybe they're conscious. Maybe they're just biological robots responding to stimuli. and for insects, 51%, barely half. A coin flip's worth of certainty. Insects have nervous systems. They respond to their environment. They learn, they remember, they make decisions. But are they aware of what they're doing? Does it feel like anything to be an ant? Half the scientists studying them aren't sure. This uncertainty reveals something important. Consciousness isn't something we can measure directly. We can't put an animal in a scanner and detect whether it's having subjective experiences. We can only observe behavior and make inferences. It's like asking who's rich enough to join an exclusive club. Where exactly is the line $1 billion, $1 million, 100,000? It's arbitrary. Someone draws a boundary, and everyone else either agrees or argues about it. The same thing happens with consciousness. We draw lines based on intuition and similarity to ourselves. Humans definitely conscious. Primates probably. Mammals mostly. Everything else, it depends on who you ask. But this approach has a glaring problem. It's biased toward things that are like us. If consciousness requires a brain structured like ours, then we'd never recognize consciousness in something fundamentally different. An alien intelligence, an AI, a distributed network, a quantum computer. We'd be looking for the wrong signs, asking the wrong questions, applying criteria that only work for carbon-based brains shaped by Earth's evolutionary history. Researchers have proposed several theories to explain consciousness, but none of them are universally accepted. Each explains some aspects while leaving others mysterious. Global workspace. Theory suggests consciousness emerges from how information is processed in the brain. Certain regions act as a central workspace where information from different senses comes together, gets integrated, and becomes available for conscious thought. According to this theory, consciousness is what happens in the brain's front office, the parts doing high-level thinking and decision-making. It explains why you can only focus on one thing at a time, why you can see either the vase or the faces in that optical illusion, but not both simultaneously. There's only so much room on the stage of consciousness. Information that doesn't make it to the workspace remains unconscious, processed in the background, but never experienced. Integrated information theory takes a different approach. It argues that consciousness arises from systems that integrate information in complex ways. The more a system integrates information, the more conscious it is. Consciousness isn't about which brain regions are active. It's about how much information is being combined and compared and synthesized. According to this theory, even simple systems might have tiny amounts of consciousness if they integrate information. A thermostat arguably has a speck of awareness, infinitesimal but non-zero. Human brains integrating vast amounts of sensory and cognitive information have consciousness in abundance. Both theories have supporting evidence. Both have problems. Neither fully explains why integrated information or workspace processing should produce subjective experience in the first place. They describe what the brain does, but not why it feels like something. And there are cases that complicate both theories. Consider blind sight. Some people with damage to their visual cortex become blind. They report seeing nothing, complete darkness, no visual experience whatsoever. But if you put them in a room with obstacles and ask them to walk across, they navigate perfectly. They don't bump into things. They step around chairs. They duck under low-hanging objects. If you ask them how they did it, they have no idea. They can't see anything. They're just guessing, they claim. But their guesses are right far more often than chance would predict. What's happening is that visual information is still reaching their brains through neural pathways that bypass the damaged regions. Their brains know what's in the room, but they don't consciously experience seeing it. The information is there being used to guide behavior, but it never reaches consciousness. So, where is consciousness in that scenario? The information is integrated. The brain is processing it and using it to make decisions, but the person experiences nothing. They're unconscious of what their brain clearly knows. It suggests consciousness is more than just information processing, more than neural activity, more than integration and complexity. There's something else, some additional factor that determines whether brain activity produces subjective experience or happens in the dark, invisible to the self. And this is where things get frustratingly vague. The more you dig into consciousness, the more elusive it becomes. Every answer raises new questions. Every theory explains some phenomena while failing to account for others. We can describe brain activity. We can map neural networks. We can correlate thoughts with regions lighting up in scanners. But we still can't bridge the gap between physical processes and subjective experience, between neurons firing and the feeling of being you. And if we can't even define consciousness, clearly, how are we supposed to know where it comes from, or whether particles themselves might have a sliver of it? If consciousness emerges from brain activity, and brain activity is fundamentally just electrical impulses traveling through neurons, then we need to ask a more precise question. How much brain activity is required before we can say consciousness exists? Think about where you feel like you are in your body. Right now, as you're listening to this, where does it feel like your consciousness resides? Look at your hands. They belong to you, certainly. You can control them. But are they where you are? Look down at your chest, your legs, your feet. Those are parts of you, extensions of your will. But they're not the location of your awareness. Most people, when they really think about it, feel like their consciousness exists somewhere behind their eyes, in their head, in their brain. That's where the you that experiences things seems to be located, and this intuition is probably correct. Remove the brain, and consciousness disappears. Damage certain parts of the brain, and consciousness changes, diminishes fragments. The evidence overwhelmingly suggests that whatever consciousness is, it's intimately connected to what the brain does. And what does the brain do? At the most fundamental level, it passes electrical signals between neurons. Sodium and potassium ions flow across cell membranes, changing the voltage. When the voltage reaches a threshold, the neuron fires, sending an electrical pulse down its axon to other neurons. Those neurons receiving the signal might fire in turn or might be inhibited from firing. Networks of billions of neurons, all signaling to each other in patterns of extraordinary complexity. That's brain activity. That's what underlies every thought you think, every sensation you feel, every decision you make. Electrical impulses racing through neural networks. So here's the question. How many neurons need to fire before consciousness appears? Do you need all 100 billion neurons in a human brain working together? Could you have consciousness with 1,000,000 neurons, 1,000, 100? What about just one neuron? If a single neuron fires, is that a tiny fragment of consciousness, the smallest possible unit of awareness, infinitesimal, but real? There's no obvious place to draw the line. You can't point to a specific number and say, below this, no consciousness. Above this, consciousness exists. It's not like there's a magical threshold at 10,000 neurons where the lights suddenly turn on and awareness begins, which raises an uncomfortable possibility. Maybe consciousness isn't an all-or-nothing phenomenon. Maybe it's a spectrum. Maybe every neuron firing contributes a tiny amount of awareness, and what we experience as human consciousness is just what it feels like when billions of these tiny conscious moments add up into something complex enough to recognize itself. And if that's true, then we can go deeper. What makes a neuron fire? An action, potential, a wave of electrical charge traveling down the cell's length. And what causes that? The movement of ions, charged particles, electrons shifting from one atom to another. If a neuron firing represents a fragment of consciousness, and a neuron fires because of electron movement, then does that mean electrons moving constitute consciousness? Are the electrical wires in your house slightly aware as current flows through them? Is every circuit, every battery, every lightning bolt a moment of primitive consciousness? It sounds absurd. Wires don't think. Electrons don't ponder existence. We don't attribute feelings to electrical current flowing through a phone charger. But if consciousness arises from electrical activity in brains, and if there's no clear threshold where electrical activity becomes conscious, then maybe everything involving moving charge has some infinitesimal amount of awareness, not enough to think or feel in any recognizable way, but present nonetheless, a fundamental property of matter and energy. Some physicists and philosophers take this idea seriously. They point out that we don't actually know what causes consciousness. We don't have a mechanism. We just know it correlates with brain activity. And if we can't explain where consciousness comes from, maybe it doesn't come from anywhere. Maybe it's always been there as fundamental, as mass or charge, present in every particle, every interaction. This is where quantum mechanics enters the picture in a particularly strange way. Remember wave function, collapse. Remember how particles exist in superposition spread out as probability waves until the moment they're observed, at which point the wave collapses into a definite state. What causes that collapse? The standard interpretation says observation does. Measurement forces the particle to choose a specific position, a specific momentum, a definite state instead of a fuzzy superposition. But what counts as observation? Does it require a conscious observer? Does the particle somehow know when it's being watched? Most physicists say no. Observation in quantum mechanics just means interaction with a measuring device, something that forces the quantum system to couple with a larger environment. Consciousness isn't required. A detector triggers collapse just as well as a conscious human looking at the detector's readout. But there's a minority view, championed by some very serious physicists, including Nobel Prize winner Roger Penrose, that consciousness and quantum mechanics might be deeply connected. That wave function collapse might be related to conscious observation in a more fundamental way than mainstream physics acknowledges. What if particles really do make a choice when they collapse? Not conscious choice in the way humans choose, but some primitive form of selection, some proto-awareness at the quantum level. It's wild speculation. There's no evidence for it, but there's also no consensus explanation for what consciousness is or where it comes from. So maybe, just maybe, consciousness goes all the way down. Maybe every quantum event, every wave collapse, every particle interaction involves a tiny fragment of awareness. And human consciousness is what happens when you get enough of these fragments organized into a complex, self-referential system. You are made of particles that constantly exist in superposition and collapse into definite states. If those collapses involve micro moments of proto-consciousness, then you are quite literally made of consciousness. Not consciousness emerging from complexity, but consciousness present from the start in every electron, every photon, every quark, all combining into the awareness you experience as yourself. Maybe the wires in your walls don't think. Maybe electrons don't philosophize, but maybe they participate in the same fundamental process that, when scaled up and organized, properly becomes thought. The same way individual water molecules aren't wet, but together they create wetness. Maybe individual particles aren't conscious, but together they create consciousness. Or maybe this is all nonsense. Maybe consciousness requires brains, period. Maybe there's a hard threshold, and below it nothing is aware, and above it awareness exists. Maybe electrons are just electrons, neurons are just cells, and consciousness is an emergent property that appears only at specific levels of complexity. We don't know, and that's the frustrating truth. Despite all our knowledge of physics and neuroscience, we still can't answer the basic question of what consciousness is or where it comes from. But if consciousness remains mysterious, quantum mechanics offers something even stranger: particles that seem to communicate faster than light-sharing information in ways that shouldn't be possible. Einstein hated quantum entanglement. He called it spooky action at a distance, and he didn't mean that as a compliment. He thought it revealed a flaw in quantum mechanics, proof that the theory was incomplete. Here's what bothered him. When you entangle two particles, their quantum states become linked. Measure one particle's spin, and you instantly know the other's spin, no matter how far apart they are. The particles seem to communicate their states to each other faster than light could travel between them. Einstein thought this proved quantum mechanics was missing something. There must be hidden variables, he argued. Secret information the particles carry with them from the moment of entanglement. They're not really communicating across distance. They already know what their partner will show when measured, because that information was determined at the start. It's like two friends going to separate bars without discussing who will pay for drinks. But somehow, every single time, one of them pays, while the other doesn't, and they never both pay, or both skip out. Impossible, right? They must have coordinated beforehand. There must be a hidden agreement. That was Einstein's intuition. The particles must carry hidden information, determining their behavior. Quantum mechanics just doesn't show us that information yet. But then, in 1964, a physicist named John Stuart Bell figured out how to test this. He devised an experiment that could distinguish between Einstein's hidden variables and genuine quantum weirdness. The math is intricate, but the concept is elegant. If particles carry hidden variables, if they have predetermined answers to any measurement you might perform, then when you measure entangled particles along different axes, you should see certain statistical patterns. Specifically, you should see matching results about 55% of the time. But if quantum mechanics is right, if particles really do decide their states on the spot when measured, you should see matching results exactly 50% of the time. 5% difference, enough to distinguish between the two possibilities. Scientists ran the experiment over and over with increasingly sophisticated equipment in laboratories around the world, and the results were unequivocal. Quantum mechanics was right. Einstein was wrong. Particles don't carry hidden variables. They genuinely decide their states at the moment of measurement. And somehow, when you measure one particle, its entangled partner instantly knows what happened and adjusts its own state accordingly. Not instantly in the sense of very fast, instantly in the sense of no time passing at all. Measure a particle here on Earth, and its entangled partner on the other side of the galaxy knows immediately. Faster than light could travel the distance. Faster than any signal could propagate through space. Information somehow traveled between the particles with no delay. This violates everything we think we know about cause and effect. Einstein's relativity says nothing can travel faster than light. Information is limited by the speed of light. Cause must precede effect, with enough time for a signal to propagate between them. But quantum entanglement doesn't care. Measure one particle, the other responds, and the response happens before light could have carried the message. Now, before you get too excited, this doesn't let you send messages faster than light. The results of measuring entangled particles are random from your perspective. You can't control what you measure. You can't encode information in the outcomes. You only see the correlation when you compare measurements afterward, and that comparison has to happen through normal, slower than light communication. So you can't use entanglement to build an Ansible or send signals into the past. The universe preserves causality barely by making the faster than light correlation useless for transmitting information. But the correlation is real. Measure one particle's spin as up, and the other light years away will measure down instantly. Not because they agreed beforehand, not because hidden variables predetermined the outcome, but because measuring one genuinely affects the other in real time across arbitrary distances. Bell's experiment proved particles are making decisions on the spot. They're not following a script written at the moment of entanglement. They're responding to measurements as they happen, coordinating with partners. They're no longer in contact with sharing information through some mechanism that doesn't involve signals traveling through space. What mechanism? Nobody knows. Quantum mechanics describes what happens, but doesn't explain how. The particles just do this. The math works. The predictions match experiments. But the underlying reality, the actual process by which one particle informs another across vast distances, remains utterly mysterious. Some interpretations suggest the particles were never really separate. Entanglement means they're still one system, even when spatially separated. Measuring one is measuring both, because there is no one and other. There's just a single quantum system extended across space. Other interpretations suggest reality doesn't have definite properties until measured. The particles don't have spins until you ask about their spins. Asking about one forces both to resolve into definite states. There's no communication because there was nothing to communicate until the measurement happened. These are interpretations, philosophical frameworks for thinking about the math. None of them change the experimental results. The particles behave the way they behave, regardless of how you interpret it. And here's what keeps me up at night. If particles can share information faster than light, if measuring one instantly affects another across arbitrary distances, then causality, the idea that cause precedes effect, that information flows forward through time at limited speed, that might not be as fundamental as we thought, which brings us to the most disturbing experiment of all, one that suggests particles might not just communicate faster than light, but might communicate backward through time itself. So, particles can communicate faster than light through entanglement. That's strange enough. But there's an experiment that pushes quantum weirdness into territory that feels impossible. An experiment that suggests particles might not just ignore the speed of light, but might ignore the flow of time itself. It's called the delayed choice experiment, and it explores a question that sounds simple, but has devastating implications. When does a photon decide whether to behave like a wave or a particle? Let me set up the experiment. You have a photon source that fires single photons one at a time. The photon encounters a beam splitter, a half-silvered mirror that reflects 50% of light and lets the other 50% pass through. When the photon hits this beam splitter, it has a choice. It can either pass straight through along path 1, or it can reflect and travel along path 2. If photons are particles, classical solid objects, then each one should randomly pick one path or the other. 50-50 odds. Each path has mirrors that redirect the photon toward a second location where the two paths converge. At this convergence point, you can choose to place another beam splitter, or you can leave it empty. Here's where it gets interesting. If you place a second beam splitter at the convergence point, the photon has another 50-50 chance of going one way or the other. You have two detectors positioned to catch the photon after this second beam splitter. If photons are just particles, randomly choosing paths, you'd expect each detector to have an equal chance of registering the photon. Simple, but that's not what happens. When the second beam splitter is present, you see an interference pattern. The photon is more likely to arrive at one detector than the other, and the probability depends on the exact path lengths in a way that only makes sense if the photon traveled both paths, simultaneously interfered with itself like a wave, and then arrived at one detector based on constructive and destructive interference. The photon went through both paths. It behaved like a wave. Now remove the second beam splitter. Leave that convergence point empty. Each path leads directly to a detector, one detector per path. If the photon arrives at the top detector, it must have come along path 1. If it arrives at the side detector, it must have come along path 2. You know which path it took, and suddenly the interference pattern disappears. Now, the photon acts like it only went down one path. It behaves like a particle, picking one route, arriving at one detector, no wave-like interference. This is already strange. The presence or absence of the second beam splitter changes whether the photon acts like a wave, going through both paths, or a particle, going through one path. The photon seems to know what configuration you've set up and adjusts its behavior accordingly. But here's where it becomes truly disturbing. What if you wait until after the photon has already passed the first beam splitter before deciding whether to insert the second one? The photon has already committed to either traveling one path or traveling both. It's already halfway through the experiment. Its wave or particle nature should already be determined. And then you decide. You randomly choose to either insert the second beam splitter or leave it out. The photon is already in flight. It's too late for it to change its behavior. Whatever it was doing, wave or particle that should be locked in. But that's not what the experiments show. In 2007, scientists ran exactly this test. They used fast switches to insert or remove the second beam splitter after the photon had passed the first one. The timing was precise. The photon was already traveling down its path or paths before the decision was made about how to detect it, and the results were unambiguous. If the second beam splitter was inserted, the photon exhibited wave behavior, interference patterns, as if it had gone through both paths. If the beam splitter was removed, the photon exhibited particle behavior, as if it had chosen a single path. The photon's behavior changed based on a decision made after it had already passed the point where that decision should matter. Think about what this means. The photon somehow knew retroactively what measurement apparatus would be waiting for it. A choice made in its future determined what it did in its past. It's like deciding today whether you want coffee or tea, and that decision changes whether you bought coffee beans or tea leaves at the store yesterday. Your choice now alters what happened before. The universe is playing a cosmic game of rewind and edit at the quantum level. Now let's be clear about what this does and doesn't mean. This doesn't let you send information backward in time. You can't communicate with your past self. The photon doesn't become a time machine that lets you change history. What it does suggest is that at the quantum level, the usual rules of causality, the idea that past determines future, and future cannot affect past, might not apply. Or at least, they might not apply in the straightforward way we assume. One interpretation is that the photon doesn't actually have a defined behavior until the full measurement is complete. It's not that the photon goes through one path or both paths and then retroactively changes. It's that going through one path versus going through both paths aren't meaningful statements until the entire experimental setup is determined. The photon exists in superposition, not just of positions, but of behaviors. It's simultaneously particle traveling one path and wave traveling both paths. Only when the measurement concludes, when the final apparatus configuration is set and the detection happens, does the photon's behavior become definite. From this perspective, there's no backward causation. There's just delayed determination. The photon's past behavior isn't set until its future measurement happens. Past and future are entangled not in time, but in definition. Another interpretation leans into the weirdness fully. Maybe information really does flow backward in time at the quantum level. Maybe the future really does influence the past, not in a way that creates paradoxes. You can't send messages to yourself, but in a way that shows causality is more fluid than we thought. The photon at the beam splitter doesn't decide what to do based on what happened before. It decides based on what will happen after. Future states determine past behaviors. Time's arrow, the forward flow from cause to effect, gets scrambled in the quantum realm. We don't know which interpretation is correct. Maybe neither is. Maybe both are useful ways of thinking about math that doesn't correspond to any classical notion of reality. What we do know is that the delayed choice experiment has been run successfully, repeatedly, with results that confirm the quantum mechanical predictions. However, you interpret it, the photon's behavior depends on measurements made after it should have already committed to being a wave or a particle. The future affects the past, or the past remains undefined until the future happens, or reality doesn't have determinate properties until observation forces it to choose. Pick your flavor of impossible. They all taste equally strange. And this brings us full circle, back to consciousness and particles and the fundamental nature of what exists. You are made of particles, electrons, protons, neutrons, quarks, photons interacting with your cells. All of them quantum entities, all of them existing in superposition until measured, all of them potentially subject to this same temporal fluidity where future and past are entangled. Every moment, the particles that constitute you are making choices or having choices made for them about where to be and what to do. And those choices might be influenced by events that haven't happened yet, by measurements in your future, by interactions still to come. Your present might be partially determined by your future, not in a grand, destiny-driven sense, but in the quantum mechanical sense, where the behavior of particles now depends on the observation states later. Causality at the quantum level is not the simple forward flow we experience in everyday life. It's tangled, bidirectional, context-dependent, and you, being made entirely of quantum particles, are subject to those same tangles. What does this mean for consciousness, for free will, for the nature of reality? Honestly, nobody knows. These are open questions. The experiments show what happens, but the interpretation, the meaning, the implications for the bigger picture, those remain deeply uncertain. But here's what strikes me as profound. We started this journey asking why photons go through two slits at once. We learned that particles are waves, that the universe is quantized, that observation changes reality. We explored how quantum mechanics both protects and threatens our secrets through encryption and quantum computers. And now we've arrived at consciousness itself, at the question of what it means to be aware, and whether awareness might be a fundamental property woven into the fabric of reality from the quantum level up. You are at the most basic level, a collection of particles that were forged in stars billions of years ago, carbon created in stellar fusion, oxygen blown out in supernovae, hydrogen left over from the Big Bang itself, stardust literally. And somehow that stardust organized itself into a pattern complex enough to look at the universe and wonder why it exists, to ask questions about consciousness and quantum mechanics and the nature of time. You are not just made of the universe. You are the universe experiencing itself. You are the cosmos looking inward matter, examining matter consciousness, emerging from unconscious elements, and asking how such a thing is possible. Every electron in your body is simultaneously a wave and a particle spread out and localized here and there now and then. Every thought you think emerges from quantum events, wave functions, collapsing particles, choosing or being chosen in patterns, too complex to fully comprehend. You are not a thing. You are an event, an ongoing process, a pattern of energy and information that maintains itself through constant change, rebuilding itself moment by moment from quantum fluctuations and molecular interactions. And somewhere in that pattern, in that endless dance of particles and waves, consciousness arose, not from outside, not from some separate realm of mind or soul, but from the particles themselves, organizing in just the right way. Whether consciousness goes all the way down to individual electrons, or whether it emerges only at certain levels of complexity, the result is the same. You exist. You are aware. You experience the universe from inside as a participant, not just an observer. Quantum mechanics has shown us that reality is stranger than we imagined. Particles go through multiple paths simultaneously. Information travels faster than light. The future influences the past. Observation changes what is observed, and consciousness, that most personal and immediate of all experiences, might be the strangest quantum phenomenon of all, not separate from physics, but emerging from it, not apart from the particles and waves, but built from them. You are stardust that learned to think, quantum events that learned to reflect on themselves, the universe looking at itself and finding the view puzzling, beautiful, and utterly mysterious. And that mystery, that profound uncertainty about what we are and why we're aware, might be exactly what it feels like when quantum mechanics operates at the scale of a human brain. When enough particles come together in the right configuration, reality doesn't just exist. It experiences itself existing. That's what you are, an experience, an awareness, a moment of the universe knowing itself, asking questions, seeking answers, and finding more questions in return. The quantum world destroys common sense. It replaces it with something far stranger and more wonderful, a reality where particles are waves, where observation matters, where past and future are entangled, and where consciousness itself might be the universe's way of exploring the impossible weirdness of its own existence. Sleep well, knowing that while you rest, the particles that make you up continue their quantum dance, spreading out as probability waves and collapsing back into definite states, existing in superposition and resolving into certainty, playing out the strange rules of quantum mechanics in every cell of your body. You're not separate from this weirdness. You're made of it. And tomorrow, when you wake, you'll reemerge from the quantum foam, those probability waves collapsing back into the pattern that is you, ready to experience another day of this strange, impossible, beautiful existence.